Data mining and warehousing. This is going to be cluster analysis, chapter 10, and we're going to discuss cluster analysis in 2 weeks. What will we cover in cluster analysis? We're going to talk about the basic concepts of cluster analysis, partitioning methods, hierarchical methods, density-based methods, grid-based methods, and evaluation of clustering. So all of these methods are actually cluster analysis methods, and for this week we're covering the partitioning and hierarchical methods. So what is cluster analysis? A cluster is a collection of data objects, examples, or instances. These objects are considered to be a cluster, they're considered to be a group because they are similar. They are related to one another, okay? And they are considered within the same group. They are also considered to be dissimilar to other objects in other groups. So to have a cluster, it means that we have a group of objects that they are similar between themselves, and they are different or they are dissimilar from objects in other groups. That's why they do not belong to the same group with the other objects in other groups. Cluster analysis, it's also called clustering, it's also called data segmentation, is about finding similarities between data objects and while considering special characteristics. These characteristics are found in the data, and probably in the data mining language, these are attributes that are found in the data, and we use these attributes or we use these characteristics to group data objects that are similar together into clusters. Clustering is considered an unsupervised learning approach. So in supervised learning, when we studied classification, we learned that the data set will have a label, and that this is a label that is given with the data set, and we use that to create a model and to train a model in order to automatically detect or future objects, future unseen objects that are not categorized, and assign them to categories or classes. However, in unsupervised learning, there are no predefined classes. We do not have labels. We do not know to what class does an object belong to. And this is what we call clustering. So clustering is actually an unsupervised learning approach. Typical applications of clustering. Clustering is used in either as a standalone tool, a function of data mining in order to get insights into data. So we want to see how many groups does the data have, or how many clusters does the data have. So in this case, we will be applying clustering, and in this case, clustering is a data mining function, just as classification. Clustering is also used as a pre-processing step. So if I want to prepare my data, in some cases we use clustering as a pre-processing step, and we're going to talk a little bit about this in a minute. Now, clustering has many applications. So, for instance, in biology, we use it to classify, to classify or to group similar species or similar animals or similar kingdoms to combine them together into clusters. In information retrieval, and which is about documents. So we will be grouping similar documents together as clusters without manually classifying them. It is also used in, let's say, in marketing. So in marketing, it's used to help identify groups of people so that we can develop targeted marketing strategies. For instance, you can identify a group of people who have interests in gardening. So you will be giving them special offers in gardening supplies or in gardening equipment. You won't be offering the same um, sale, or you won't be marketing or, the same products to all your customers. You will be targeting these customers who you identified as a cluster. And it has many and many other kinds of applications. You could look at them and you can read them and you can expand your knowledge by probably read more um, research about clustering and uh, its applications. Now, when we talk about clustering as a pre-processing tool, we already gave this as an example when we talk about getting to know your data. So it is used for summarization, compression, finding k-nearest neighbors, and also in outlier detection. In summarization, we use it when we want to do pre-processing for regression, PCA, also for classification, or in association analysis. Compression is actually an application of image processing. So we use clustering to compress, to make the images have um, um, less size. Also, it is used to find objects that are close to each other, finding k-nearest neighbor in order to localize search. So instead of searching the whole um, data set, we'll be searching in a subset of the data set. Also, it is used in outlier detection because outliers can be thought of as objects that are far away from all other objects. So this is clearly an outlier. Quality. When we talk about quality of clustering function, we are considering that a good clustering method should produce high quality clusters, meaning that the cluster will have high intra-class similarity, which is called cohesive, which means that a good cluster will have the objects within the cluster will not be far away from each other. Okay, so they will be highly similar, and we will have a low interclass similarity, meaning that the similarity between the two classes or between the two clusters is low. They're not similar, they're far away from each other, and this is called distinctive. So if we can identify clusters that satisfy these two conditions, this means that we actually have a good cluster. The quality of clustering method depends on the similarity measure, so and the distance between objects, either within the same cluster or or between the clusters. How it's implemented, how is the clustering method implemented, and the ability or its ability, the clustering method's ability to discover some of the hidden patterns. So the clustering method should be able to uncover uh, objects that are similar but are not clearly similar. So if it's able to identify that, then it is a good clustering method. The similarity and similarity metrics, we already spoke about that, and we said that distance measures is actually the similarity and similarity is expressed in a distance function, and distance function are different depending on what type of data we are dealing with. We studied how Boolean and categorical and ordinal data, how do we calculate the distances between them. So it is the way we calculate distance between the different types of variables is different. Weights should be associated with different variables based on applications and data semantics. So the weight of similarity um, uh, is important based on what type of variables we're discussing. Now, quality of clustering, when we say that this is a good clustering method, or this is a good cluster, um, it is it is very hard to say how good is it, and it's actually highly subjective. It depends on what's the application, on what are we using our clustering method. What is the application? What is the objects that we're using? So there is no clear-cut quality measure for clustering. It's highly subjective. Now, when we talk about cluster analysis, we said that we have different ways. First of all, when we talk about partitioning, clustering as partitioning a method, we need to discuss what is the partitioning criteria. How are we partitioning the objects? Do we have a single attribute that based on that we're partitioning the objects, or do we have hierarchical partitioning? Do we have multi-level hierarchical partitioning? Do we have a single level or a single attribute partitioning? Also, the separation of clusters, is it exclusive or non-exclusive? Exclusive separation means that, for instance, one object will be belonging only to one cluster. It cannot belong to multiple clusters. Or non-inclusive, meaning that it can belong to multiple clusters or classes. The similarity measure used, it can be distance based or connectivity based. Distance based, we already studied the Euclidean distance. There are others such as road network or vector. And we have the connectivity based such as the density or contiguity. Clustering space also, if we have a full space of clustering, or we have subspaces. So usually the full space is low dimensional, very few attributes, and subspaces will have high dimensional clustering. Okay, when we talk about the types of clustering approach, we said that we have partitioning approach, we have hierarchical approach, we have density-based approach, and we have grid-based approach. We're going to discuss partitioning approaches first. And the aim of partitioning approach is to construct various partitions, various sections, clusters, and then evaluate them based on certain criteria. Okay, in mostly we want to minimize the sum of square errors. So this is one way of evaluating partitioning clustering uh, functions. Methods under this type is the k-means and k-medoids. We're going to talk about them, and we have the Clarence. Hierarchical approach is to create a hierarchical decomposition, and we'll see that in a minute, okay, of the data set using some criterion. Examples is Diana, Agnes, there's Birch and Chameleon. And there's also density-based approach, which is based on connectivity and density functions, such as dbScan, optics, and densclu. And we also have the grid-based approach, which is based on multiple level granularity structure, such as thing, wave, cluster, and click. And we're going to talk about, as I said, partitioning option first. Now, this is partitioning or clustering. This is how to partition clusters. So this is the data set, original data set, okay? And now we want to identify clusters. So the algorithm was able to identify 3 clusters. So there are 3 groups of objects here. This is a hierarchical cluster, which means that this is traditional hierarchical clustering. So it means that these belong to this cluster. However, P4, P3, and P2, they all belong to the other one, to the wider one, and we have the bigger cluster where all objects belong to it. This is a traditional dendrogram representing that P and 3 is the same here. P and 3 belong to the same cluster. 4 will be belonging to along with them in this cluster, and we also have this cluster combining everything. Partitioning algorithms. So partitioning methods is actually trying to partition a data set D which contains number of objects into K clusters. In order, or the aim of this partitioning method is to have the sum of square distances, minimized. So the sum of square distances minimized. The square distances is between the object and the centroid or middoid, and we're going to talk about the difference in a minute between each one of them. So let's look at that here in the evaluation criteria. This is the purpose of having a partitioning algorithm. So we have the sum from I1 to K. K is the number of clusters targeted, okay, and the sum where P belongs to CI. P is the object, okay, and belongs to CI. CI is the centroid or middoid of a certain cluster. So each cluster will have centroid or middoid, and these are belong to, so each cluster will have only one, either a centroid or a middoid, and sometimes we use centroids and sometimes we use middoid. Now P, which is the object, minus C, which is the centroid or middoid, when we minus them like this, it means the distance. So P minus C is the distance between the object and the centroid, okay, squared. So this is what's meant here, the sum of square distances. Now, given K, find a partition of K clusters that optimize the choosing partition criterion, where we want to have a K clusters. So K represents the number of clusters that we want to have. And we want this to have or to be global optimal, meaning that it is a solution for all objects. It includes all objects. We apply a heuristic method. This can be k-means or we have k-middoids algorithms, and we will explain the difference between them in a minute. Now, k-means each cluster is represented by the center of the cluster, and k-middoid, each cluster is represented by one of the objects in the cluster. Now, the k-means clustering, which is the most it is the most known clustering method, okay, it's implemented in 4 steps. First of all, we partition the objects into k non-empty subsets. So we randomly divide the objects in the dataset into k non-empty subsets. Then we compute seed points as the centroids of the cluster. So for each cluster, we compute a seed point, and this is considered to be the center of the cluster of the current partitioning. So we will compute the center. We will find a point at the center of the cluster, and we call this a seed point. Now this seed point can change along the way. Can't change along the way. So this is the cluster of the current partitioning, okay? And the centroid is the center, the mean point of the cluster. Now, we assign each object to the cluster with the nearest seed point. So after we identified a seed point, now we assign each object to the nearest seed point to it. Now, once we go back to the second step, when we recompute again the seed point, when we stop when the assignment does not change. So we recompute the seed points again when we have a new set of clusters. Right. So these are the steps. This is the data set. And we said that the K will be 2. So it's an arbitrary partition objects into K groups. So we'll be identifying two groups just without really considering, without any considerations, just arbitrarily. Now, we say that these objects belong to this group and these objects will be belonging to this group. Then we will identify the seed points or the cluster centroids. So this point is this cluster centroid, and this point is this cluster centroid. Now we'll be calculating the distance between each object and this centroid and assign objects accordingly. After doing this, we will find that this object here is closer to this centroid than this centroid. So this object will be belonging to this group. Okay, so when we do that, we will find that these also here, this object here is closer to this object, to this centroid than this centroid. Okay, so when we do that, we find that these will actually belong to this centroid, and these sorry, to this cluster, and these will be belonging to this cluster. Okay, and then again we will be calculating um, uh, the cluster centroids, and if we need to loop again and identify new cluster centroids until we finally end up with unchanged groups of clusters, then it's considered finished. Now, these are the same steps. So partition objects into K non-empty subsets. Repeat. This is the repeat part. Compute centroid mean point for each partition. Assign each object to the cluster of its nearest centroid. And then we keep repeating until nothing changing. The strength of k-means clustering is, first of all, it's efficient. Its big O notation is T multiply K multiply N. N is the number of objects, K is the number of of clusters, and T is the number of iterations, the number of the times that the loop is repeated. And normally K and T are way less than the number of objects. Comparing this big O notation to a partitioning around midoid, it's actually big O notation of K multiplied by N minus K to the power 2. Clara, big O notation of K multiply S to the power of 2 plus K multiply N minus K. So definitely, if you remember with big O notation, 2 is considered to be way higher than having a 1. Weaknesses of k-means method is that it's only applicable to objects in continuous n-dimensional space. So meaning that we can use it actually in numerical data. Okay, and also we can use it for categorical data because we can change categorical data into numbers, because k means needs, in order for it to calculate, it needs to have numbers. You cannot calculate the mean of a textual uh, attribute. Now, when we are using categorical data, it's called key. We can use K mode. So instead of K means, it will be K mode clustering. In comparison, the K-medoid can be applied to a wide range of data types. We need to specify how many clusters do we have. So there are ways to do that. There are ways to identify the optimum number of K, such as using silhouette, for instance. but it's usually a challenge to identify the correct number of k that is suitable to your data set. It's also, k-means is very sensitive to noisy data and outliers, and k-means is not suitable to discover clusters with non-convex shapes such as this. So if the cluster looks like this, k-means is not efficient in this case. Variations of k-mean method. Um, so most of the variants of k-mean method will differ in how k is selected, the selection of k-means, how at the beginning, uh, what kind of similarity calculations used, and what are the strategies to calculate the means, the cluster means. And as I just said, when we're handling categorical data, we use k-mode. So instead of using the mean, we'll be using the mode. Also, we can use new dissimilarity measures in order to deal with categorical objects, because the similarity measures of categorical objects is different. And we can also use frequency-based methods to update modes of clusters. Instead of calculating distance, we calculate how many objects are there. And when we have a mixture of categorical and numerical data, we can use the k-prototype method. So this means that we have k-means clustering, k-modes clustering, and here we have k-prototype method. All of them are variations of k-means. What is the problem of k-means method? As I said, it's sensitivity to outliers. Um, so if an object with an extremely large value can actually easily distort your calculations, because you're calculating based on the means. However, if you use the k-medioids, instead of taking the mean value of the object in the cluster as reference points, you will actually be using medioids. You will be using objects within the cluster, which is will be the most centrally located object in the cluster. So in k-means, we use a seed point, which is an arbitrary point in the middle of the cluster. It's not an object. But in the k-medioids, we actually use an object which is in the center of the cluster. This is the main difference between k-means and k-medioids. Okay, so these are two groups of or clusters. This object here is considered to be in the k-medioid because it is in the center, and here it's an object. So in the medioids, using the k-medioids, we actually looking into objects from the data set. In the k-means, we are calculating a point in the middle of the cluster, not belonging to the data set. Partitioning around medioid. So a typical medioid algorithm. So this is the data set. K equal to arbitrary choose K as an object. We will choose an object to be the one in the middle. Okay, and then we will assign the remaining objects based on their distance from the medioid, and then randomly select a non-medioid object O. So we will select O, okay, and we will calculate the distance between O from the first medioid and O from the second medioid, okay. And if we find that O, the current cluster of O is further from O compared to the other object, O will be moving to the other what do you call it, to the other cluster. Otherwise, it remains the same. So we compute the total cost of swapping, meaning that we will compute if O is actually belonging to this cluster, it's better for it to be belonging to this cluster or to this cluster. And we do loop until no change. Okay. The k-medioid clustering method. First, we need to find the representative objects, object, or it's actually object per cluster, medioid in clusters. And we will identify, it's called as PAM, or partitioning around medioid. Starts from an initial set of objects or medioids, and iteratively replaces one of the medioid by one of the non-medioid if it improves the total distance of resulting cluster. PAM works in small data sets, so it's better with small data sets because of the computational complexity, computational time. It's highly costly algorithm compared to K clustering, K means. And efficiency improvement of PAM. Clara is actually an improvement on PAM, where PAM is actually PAM on samples. And CLARANS is also another improvement of PAM, where we use a randomized resampling approach. I will stop here for the first hour of the lecture, and in the next hour, we'll talk about hierarchical clusters.